Good morning, students. Today, we are going to dive into the fascinating world of circuit theorems, KVL and KCL. These concepts are the building blocks of electrical engineering, and understanding them is crucial for analyzing and designing electrical circuits. So, let's embark on this enlightening journey together. Circuit theorems and Kirchhoff's laws are fundamental principles that allow us to unravel the mysteries of electrical circuits. They provide us with the tools to simplify complex circuits and solve intricate problems. By grasping these concepts, you will gain a solid foundation in circuit analysis and be well equipped to tackle more advanced electrical engineering topics. In this session, we will understand the following concepts, namely dependent current and voltage sources, node and mesh analysis, current and voltage divider rules, superposition theorem, Thevenin's theorem, Norton's theorem, maximum power transfer theorem, reciprocity theorem, compensation theorem, concept of duality and dual networks. So, let's begin our journey. We will focus on four types of sources: independent current sources, dependent current sources, dependent voltage sources, and independent voltage sources. Let's begin with independent current sources. An independent current source is a device that provides a constant regardless of the circuit parameters or other elements. It is represented by a symbol consisting of a circle with an arrow pointing inward or outward, indicating the direction of the current flow. Independent current sources are widely used in various applications, such as electronics, power supplies, and amplifiers. Moving on, we have dependent current sources. Unlike independent sources, dependent current sources are controlled by the behavior of other components in the circuit. They can be expressed as a function of volt or current in another part of the circuit. The symbol for a dependent current source is similar to that of an independent current source, but with an arrow labeled with a controlling variable or equation. Dependent current sources play a crucial role in circuit analysis, allowing us to model and simulate complex circuit behaviors accurately. Next, we have dependent voltage sources. Similar to dependent current sources, dependent voltage sources are controlled by other circuit parameters. These sources can be expressed as a function of voltage or current in other parts of the circuit. The symbol for a dependent voltage source consists of a diamond shape with a controlling variable or equation labeled inside. Dependent voltage sources are widely used in various circuit designs, such as voltage regulators, oscillators, and sensors. Lastly, we have independent voltage sources. An independent voltage source is a device that provides a constant voltage regardless of the circuit parameters or other elements. It is represented by a symbol consisting of two parallel lines, one longer than the other, with plus and minus signs indicating the polarity of the voltage. Independent voltage sources are crucial in powering various electrical circuits, such as electronic devices, lighting systems, and battery-powered applications. Understanding the differences and applications of these sources is vital for circuit analysis, design, and troubleshooting. By grasping the concepts of independent and dependent sources, we can accurately model and simulate circuit behavior, predict voltage and current distribution, and analyze the performance of various components. Node analysis and mesh analysis. These methods, based on Kirchhoff's current law, KCL, and Kirchhoff's voltage law, KVL, respectively, provide us with systematic approaches to solve complex circuits. Let's begin with node analysis. Node analysis is a method that allows us to determine the voltage at various nodes in a circuit. A node is a point in the circuit where two or more components are connected. By applying Kirchhoff's current law, KCL, which states that the sum of currents entering a node equal to the sum of currents leaving that node, we can set up a system of equations to solve for the unknown node voltages. Node analysis is particularly useful when dealing with circuits that have multiple voltage sources, as it provides a straightforward approach to determine voltage distributions. Moving on, we have mesh analysis. Mesh analysis is a technique that enables us to determine the currents flowing through different loops or meshes in a circuit. A mesh is a loop that does not enclose any other loops. By applying Kirchhoff's voltage law, KVL, which states that the sum of voltages around any closed loop is zero, we can set up a system of equations to solve for the unknown mesh currents. Mesh analysis simplifies the circuit analysis process, especially for circuits with multiple sources, and allows us to determine current distributions accurately. Both node analysis and mesh analysis provide systematic and efficient approaches to analyze circuits. They offer us a way to simplify complex circuits by breaking them down into smaller components, solving for unknown variables step by step. By applying these methods, we gain a deeper understanding of circuit behavior and can accurately determine voltage and current values. KVL statement. The sum of voltages around a closed loop is equal to zero. Mathematically, we can write as mentioned in the slide, sigma of voltage around a closed loop equals to zero. The term around a closed loop means that you travel around the circuit and start and stop at the same location. The sum of the voltages across the elements that you travel through, any path you choose, will be equal to zero if the starting and ending points are the same. These are the steps and checkpoints while performing a KVL calculations. Write the polarity, plus and signs, across every element in the circuit. For voltage sources, the polarity is set by the battery symbol, plus sign on the long end line. For resistors, the plus and signs are written in the direction of the assumed current flow. For current sources, the head side of the arrow has the plus sign. Start at a point in the circuit and travel around any path you choose until you get back to the same starting point. As you're traveling around the path, you write down the voltage of the elements you go across using the sign that you travel through. If you travel into the plus sign, the voltage term is positive, and if you travel into the sign, the voltage term is negative. If you have only one unknown, the KVL equation for that unknown. If you have multiple unknowns, you will need to obtain additional KVL and/or KCL circuit equations or other information to solve for them. If your calculation yields a negative current, that means you assumed the current in the wrong direction. The current magnitude is correct, but the direction needs to be changed. Resolving the circuit is not necessary if the wrong direction is assumed. In this slide, let us understand mesh analysis with a very simple example. Here, voltage source of 12 volt is given, which is connected to the series connection of 5, 10, 20 and 25 ohms. Here, we are given task to find the value of the volt across R4 using KVL. So, let's begin. First, we will observe that in this given circuit, only one loop is present, so only one equation shall be created. Now, let's create one equation for the same. Here you can see that I have -12 because if we go clockwise in the circuit, the first sign that we touch in case of battery is minus. Then we have written 5 into I of s plus 10 into I of s plus 20 into I of s plus 25 into I of s equal to 0. After that, we have taken 12 on the right hand side of equal sign and taken I of s common from all. After that we have divided all other terms keeping I of s on left side, and as a result we get I of s equal to 0.2 ampere. Here we also see that the direction of current that we took, which was anticlockwise in our case, stands true because our answer is also positive. Now to find voltage across R4, we multiply current with value of R4 and get 5 volts.